What if the most mysterious objects in the universe, the black holes we thought we understood perfectly, have been hiding a secret layer of complexity all along? For decades, physics textbooks have taught us that black holes are simple, bald entities defined only by their mass and spin, stripped of all other details. But what if that simplicity was just an illusion created by the rigid assumptions we made to make the math easier? Welcome to a fresh look at the cosmos, where we challenge the static view of reality and uncover a dynamic universe teeming with hidden interactions. Today, we are diving into 3 groundbreaking shifts that are reshaping our understanding of gravity, from the nature of black holes themselves to the very fabric of spacetime and the tools we use to simulate it. You will learn how relaxing old rules opens up new frontiers in gravitational wave detection, how a subtle change in a cosmological model resolves a decades-old puzzle about neutrinos, and why a new computer code is becoming the gold standard for accuracy. Stay until the end because these theoretical pivots are not just abstract math. They are the keys to unlocking the next generation of discoveries in the millihertz gravitational wave sky. For a long time, our understanding of black holes was governed by strict, no-hair theorems. These mathematical rules told us that black holes were bald, meaning they could not support any external fields or hair around them. This view relied on 2 very specific, rigid assumptions: that the universe is asymptotically flat at great distances, and that these objects exist in a stationary, unchanging state. While these assumptions made the equations solvable, they also painted a picture of a universe that was perhaps too clean, too idealized, and disconnected from the messy, dynamic reality we actually observe. This rigid framework created a barrier, effectively ruling out a vast parameter space of ultralight black holes and limiting what we thought was possible to detect in the low-frequency bands of gravitational waves. Similarly, in cosmology, the standard model struggled with a strange tension. Calculations kept producing unphysical negative masses for neutrinos, a result that simply didn't make sense in the real world. We were stuck with models that were mathematically elegant, but physically incomplete, leaving us unable to fully interpret data from upcoming massive surveys or to trust our simulations when scaling up to the complexity of the entire universe. But now, a wave of new research is breaking down these barriers, revealing a universe that is far more hairy and interconnected than we previously imagined. By relaxing the strict assumptions of asymptotic flatness and stationarity, scientists have discovered that black holes can indeed support external fields, effectively giving them hair. Imagine a star that isn't just a smooth, featureless sphere, but an object surrounded a complex, dynamic atmosphere of matter and energy that interacts with its surroundings. This shift in perspective reopens the door to detecting ultralight primordial black holes in the millihertz frequency range, a band of the gravitational wave spectrum that was previously considered barren and silent. At the same time, a new cosmological model known as the sign-switching cosmological constant is resolving that confusing neutrino mass tension. By allowing the cosmological constant to switch signs, this model yields a physically consistent, effective neutrino mass of roughly 0.055 electron volts, finally aligning theory with observation. Furthermore, this new era of discovery is being built on a foundation of rigorous numerical validation. The Jinkaku N-body code, a powerful new simulation tool, has achieved sub-1% agreement with established codes like Gadget and Ramses. This incredible level of precision validates our emulators, ensuring that the complex simulations we run to model galaxy formation and gravitational waves are reliable and consistent. The implications of these findings ripple far beyond pure theory, fundamentally altering the landscape for science and technology. In the realm of gravitational wave astronomy, reopening the parameter space for ultralight black holes means that detectors like LISA and pulsar timing arrays now have new targets to hunt for in the low-frequency sky. We are no longer blind to a whole class of cosmic events that were previously hidden by our own theoretical constraints. In cosmology, the resolution of the neutrino mass tension provides a robust framework for interpreting the Dell flood of data expected from next-generation surveys like DAISY and Euclid, allowing us to decode the history of the universe with greater clarity. For engineers and computational scientists, The validation of high-precision tools like Jinkaku ensures that the complex models driving mission-critical trajectory planning and data analysis pipelines are trustworthy. We are moving from an era of rigid, idealized approximations to one of dynamic, interaction-rich frameworks that better reflect the true complexity of nature. This shift empowers us to ask deeper questions about the specific observational signatures that distinguish these hairy black holes from background noise, and to explore how the cosmological constant might have evolved over cosmic time. As we stand on the brink of this new era, the universe feels both more complex and more knowable. The relaxation of old rules has not created chaos. Instead, it has revealed a richer tapestry of physical phenomena waiting to be explored. From the hairy black holes whispering in the millihertz band to the consistent mass of neutrinos shaping our cosmic history, these insights provide the solid ground we need to build the future of astronomy. Thank you for joining us on this journey through the evolving cosmos. If you found this deep dive into the hairy universe as enlightening as we did, please like this.